Hi, welcome to section 8.3, and the title of this section is trig substitutions. And in this section there are 3 different trig substitutions that you can use depending upon what the integrand looks like. The first part of my presentation is going to deal with one of the substitutions, and that will be when we use the tangent. So here we have a picture of what you see in your book. And you have some nice pretty right triangles drawn, and right now maybe this doesn't make too much sense to you, but what we're going to look at right now is this very first triangle, and that will involve a substitution that deals with the tangent. So let's see where we're going to go with this. Now I do have a word of caution though, however, and that is that not every integral that contains one of these square roots that you see here, here, or here will involve a trig substitution. And a trig substitution usually takes more work than other methods. So if you don't have to use a trig substitution, then don't use one. For example, here we have the square root x squared minus 16. But this is not an integral that would involve a trig substitution because I have an x out here. And this is really of the form u to the n du. Because if u is equal to x squared minus 16, then du is 2x dx. I have the x and the dx, and all I need to do is compensate for that missing factor of 2. So you would not want to use a trig substitution on this. Down here I have another example of where you would not want to use a trig substitution. Here you have a square root, 4 minus 9t to the 4th, but if I consider 9t to the 4th as 3t squared quantity squared, then I have my 3t squared here, and the derivative of that is 6t. I have a t up here in the numerator, so that would make this right here, this integral, of the form inverse sine. So here's 2 examples where you would not immediately want to jump into it and use a trig substitution. So be careful of that, because as you work through the problems in the text, you'll find some that require trig substitutions interspersed with some that do not. And you need to know when you should use one and not. But here, let's look at a problem now where you would definitely use a trig substitution. Okay? Let me cover over this picture right now, and let's look at this example right here. You want the antiderivative of 1 over 7 plus 9t squared dt. This is how we're going to go about working it. Now in your book, you'll see this right triangle, and it says if you have an integrand that involves something like a squared plus x squared, the substitution you're going to want to use is x is equal to a tangent theta. So now let's break all of this up into pieces so we know what's going on. A squared is clearly 7. See, I have 7 plus 9t squared. And then x squared is 9t squared. And so that makes x equal to 3t. Now later on I'm going to need dt. So I will now set 3t right here equal to the square root of 7 tangent of alpha. I'm using alpha. It was easier for me to type than theta. I'm using word. That's the only reason. So theta right here is the same as alpha. All right, now I'm going to return to this triangle that you're going to see on the next page in just a little bit. But here's what I have set up for you now. Okay, here's alpha. And the tangent of alpha is 3t over the square root of 7. See, we can see that from this particular statement. And if that's the case, then I can just use the Pythagorean theorem to get the hypotenuse, and that would be the square root of this squared, and that would be 7, plus this squared, which would be 9. Whoops, I guess that should be a t right here, huh? Not an x. So I have now the square root of 7 plus 9t squared, and I have my right triangle complete. Now I'm going to come back and use this triangle when I get my final answer. So like I said, we'll come back to it. Okay, so now we need to get some derivatives. If you remember, in our original integral we had dt, and so we're going to need to replace dt in terms of alpha. So here we have, I take the derivative here, and I get 3 dt, and then I take the derivative of the right-hand side, and I get the square root of 7. The derivative of the tangent is the secant squared, and then times d alpha. We will need that when we make some substitutions. Okay, let's see what we have here. So now our original integrand, remember, is this thing. 1 over the square root of 7 plus 9t squared. Let's look at the denominator first. Okay, 7 is clear. And then remember I made the substitution for 3t was the square root of 7 times the tangent of alpha. So now this becomes 7 tangent squared alpha. And then dt, if we go back and look at the previous example right here, we had 3 dt was the square root of 7 secant squared alpha d alpha. So dt would be 1/3 of this. And you're going to see that right here in the numerator. Now, to go from this line to this line, all I did was rewrite it so it made a little bit more sense. I brought the 1/3 out in front, and you can see this numerator is the same as it was. And then I have 1 over this denominator right here. The only thing I did to go from this line to this line is I did factor out a 7. So this becomes now 7, 1 plus tangent squared alpha. Okay? Now, what do I have here then? Well, the numerator stayed the same. 1/3 square root of 7 secant squared alpha d alpha. And then I have 1 over. Now remember I had that square root, so that's the square root of 7. And then I had 1 plus the tangent squared alpha, which is secant squared alpha. And the square root of the secant squared alpha is the secant of alpha. Notice I have the square root over 7, but I do not have it over the secant. Well, this is looking good. Look, because the secant squared alpha over the secant of alpha gives me the secant of alpha. The square root of 7 cancels with the square root of 7. So I have 1/3, bring it down here, secant alpha d alpha. Like I said, looking way better than it did just a few pages ago. So now let's take the antiderivative of what I have here. 1/3 the secant of alpha d alpha, we know is 1/3 the ln of the secant of alpha plus the tangent of alpha. All right, now we're not quite finished yet because remember our original problem was in terms of t. So let's go back to this picture that I said was important before. Okay, here I have alpha, remember, and then the sine of, the tangent of alpha was 3t over the square root of 7. And then this was my hypotenuse. I remember I made some comments about that previously. So now we need to know what the secant of alpha and the tangent of alpha are both equal to. Now remember, the secant is equal to the hypotenuse over the adjacent. So the secant of alpha, and again, this should be a t, sorry about that, okay? The secant of alpha should be 7 plus 9t squared divided by the square root of 7. And the tangent of alpha, remember, is the opposite over the adjacent. So the tangent of alpha is 3t divided by the square root of 7. Now what I'm going to do is I'm going to take both of these and substitute them into that temporary answer right there. Okay, and this is what I'm going to get. I'm going to get 1/3 ln, remember that's the secant, and this is the tangent, all right, plus c. Now how did I go from here to here? What happened to the square roots of 7? Well, I can add these two in here since they have the same denominator, and that is the square root of 7 plus 9t squared plus 3t all over the square root of 7. Then I can use a property of the ln and say that that would be the ln of the numerator, and that's how I have it down here, minus the ln of the denominator, and that would be minus the ln of the square root of 7. But the square root of 7 is just another constant, so I lump it into this arbitrary constant right here. And it's not that I'm just erasing them, but remember, this is not a particular value c. Even though we say plus c, we mean any constant. So I can lump the square root of 7 into this constant right here and rewrite my final answer as what you see right here. 1/3 the ln of this absolute value plus c. So I'm going to quit this video right now, and the next one that you see, I will work one of the problems that deal with sine, a substitution that involves sine, and then one that involves the secant. Okay, bye-bye.